All right, part B asks us to find the expectation value of x, x squared, and then the standard deviation, or the uncertainty in x. So first, let's find the expectation value of x. So the expectation value of x is given by the integral from negative infinity to infinity of x rho of x dx. So let's just substitute in rho of x, and I'll pull out the a. We'll get the integral from negative infinity to infinity of x e to the minus lambda x minus a squared dx. And now we can actually just let z equal x minus a, so dz equals dx, and x equals z plus a. And now just make these substitutions into the integral, so we get a integral from negative infinity to infinity of z plus a e to the minus lambda z squared dz. And then we can just separate this into two separate integrals. We get a times the integral from negative infinity to infinity of z e to the minus lambda z squared dz, plus the integral from negative infinity to infinity. I'm going to pull out the a of e to the minus lambda z squared dz. And this first integral right here, we see that z is an odd function and e to the minus lambda z squared is an even function, and an odd function times an even function yields an odd function. And an odd function integrated over all space has to be 0. So this term right here is actually 0. So this term is 0. And then this term, we've actually done this integral quite a few times. This integral is equal to root pi over lambda. So all we get here is that a times root pi over lambda is equal to the expectation value of x. So a, again, is root lambda over pi times root pi over lambda times a equals the expectation value of x. And so we find that the expectation value of x is equal to a. That's the first part of part B. The second part of part B asks us to find the expectation value of x squared. So let's go ahead and do that now. So the expectation value of x squared is equal to the integral from negative infinity to infinity of x squared e to the minus lambda x minus a squared dx. So we can actually just let z equal x minus a again, and then dz equals dx, and x equals z plus a. So let's go ahead and substitute this back in, and we get a times the integral from negative infinity to infinity of z plus a squared e to the minus lambda z squared dz. And now let's go ahead and separate this into three separate integrals for the three terms that we get when foiling this out. So we get a times integral, the first integral, which is integral from negative infinity to infinity of z squared e to the minus lambda z squared dz, plus the integral from negative infinity to infinity of, there's going to be a 2a, and then a z e to the minus lambda z squared dz, plus an a squared from the foiling, integral of e to the minus lambda z squared dz. And this integral right here is 0 for the same reasoning that this integral was 0, because the integrand is odd and we're integrating over all space. And this integral, once again, we've done multiple times, it's root pi over lambda. So we've already found these two integrals just by observation, and all we need to calculate is this first integral, which I'm going to let be equal to I. Is integral from negative infinity to infinity of z squared e to the minus lambda z squared dz. Now, we can actually solve this using Feynman's method. So we can say that the integral from negative infinity to infinity of e to the minus lambda z squared dz is equal to root pi over z, as we know. And we can differentiate both sides with respect to lambda. Sorry, that should be a lambda. So if we differentiate both sides with respect to lambda, we can bring this into the integral and differentiate this term, and the z squared we just treat as a constant. So what we get is a negative z squared e to the minus lambda z squared dz, and then there's an integral over here. And then the right hand side, we just have root pi over, times lambda to the minus 1/2 power. So when we differentiate that, we get root pi times -1/2 lambda to the -3/2 power. So we can actually just cancel out these negative signs. And then we see that on the left we get this integral, which is just c squared e to the minus lambda z squared dz. And that's equal to root pi over 2. And then we can actually just pull out a lambda and simplify it like this so that it looks much nicer. 1 over 2 lambda root pi over lambda. So we see that on the left-hand side, this equation is exactly what this equation is. So we found the value of this equation, it's this. So we know that I is equal to 1 over 2 lambda root pi over lambda. So now all we need to do is just substitute this value in here, and this is 0, and we know this value, and then we just multiply it all by a. So the expectation value of x squared is going to be a times, and we can actually just take this root pi over lambda to be 1 over a. So let's just let this be equal to 1 over 2 lambda times 1 over a. So that means that we get 1 over 2 lambda times 1 over a plus 0 for this middle integral, and then plus a squared times 1 over a. So when we bring in the a, this cancels with that and that. So we're just left with 1 over 2 lambda plus a squared, the expectation value of x squared. Okay, and then for the last part of part B, we just need to find the uncertainty, which is given by the expectation value of x squared minus the expectation value of x quantity squared, square rooted. And the expectation value of x squared we just found, it's 1 over 2 lambda plus a squared. And we have to subtract off the expectation value of x squared. So for that, we would just need to square both sides here. And we're just left with a squared. So minus a squared. And there's a square root here. I hate when it does that. There we go. And then, so this will cancel with that, and we will be left with the uncertainty, which is equal to 1 over 2 lambda, or 1 over root 2 lambda, if you want to write it slightly better. So that's the final answer for part B. And real quick, part C is pretty fast. It just asks us to sketch the graph of row of x. So the graph of row of x is going to look something like this. It's a Gaussian distribution, so it'll have that general shape, but you see that when x equals a, row of x is maximized. So when x equals a, this whole exponential term is 0, e to the 0 is 1, so row sub x is maximized when x equals a. So when x equals a, this is going to peak, and it's just going to be a Gaussian distribution like this. And if we integrate this over all space, we should get 1. So yeah, that's what row sub x looks like. Yeah.